Okay, so in this problem, we're asked to find the cube roots of 8. We start by putting it in polar form. To help there, you realize that this is 8 plus 0i. There's no imaginary part, so we just kind of put in 0 imaginary part. That means the radius is 8, and the distance that this is above the x-axis, the real axis, is 0. So putting it in polar form, you get 8 times cosine of 0 plus I times the sine of 0. And we want to find the cube roots of that. So that means n equals 3. I'm going to put this into our formula for roots. The one in degrees is here, the one in radians is right here. And I can zoom in a little bit on that, make it a little clearer. Theta is 0, 360 times k divided by n is 3, cube root of 8. Got everything. Now, let's simplify this a little bit before I start putting in different values for k. Cube root of 8 is 2. 0 plus 360k, well, it's really 360k over 3, or cosine of 120 times k, plus I times the sine of 120 times k. And that's z sub k. Now that formula is good for k starting at 0, 1, 2, all the way up to n minus 1. Well, 3 minus 1 is 2. So for k equal 0, 1, and 2. I'll go back when we're done. So let's start by putting in a 0 here. Z sub 0 is going to be 2 times the cosine of 120 times 0 is just going to be 0, plus I times the sine of 120 times 0 is again going to be 0. Now we can simplify that. That's going to be 2 times, what's the cosine of 0? It's going to be 1. Plus I times sine of 0 is 0. So this is really 2 times 1, or 2. That's the root that we're all familiar with. But there's 2 more. Let's try and find z sub 1. So z sub 1 means I'm going to put a 1 in here for k. So it's going to be 2 times the cosine. Well, 1 times 120 is just going to be 120. Plus I times the sine of 120. And these are numbers you can get off your unit circle. Cosine of 120 is going to be negative 1/2, plus I times the sine of 120 is going to be square root of 3 over 2 times I. And when I distribute the 2, those denominators disappear. I get negative 1 plus the square root of 3i. So that's your rectangular coordinates. You could put 0i here if you wanted to or need to. I don't know what my math lab is going to demand. It might want the real and imaginary part. I'm not sure. Okay. Last one of these. Remember, k goes up to n minus 1. So n minus 1 is 2. See if you can't fill in this last part. Plug in k equal 2. See if you can't simplify it. You should get something similar to this, but not exactly like this.
Okay.
So if I plug in a 2 here, 2 times 120 is going to be cosine of 240 plus I times the sine of 240 equals 2. What'd you get for the cosine of 240? And the sine of 240? And when I distribute here, I get -1 minus the square root of 3 times I. So those would be all 3 of your cube roots of 8. All 3 of these. Now there's an interesting thing that happens when you plot these. If you were to plot them on the complex plane, here'd be your 2 plus 0i. It'd be on a circle of radius 2. And then -1 plus square root of 3i would be up here, and -1 minus square root of 3i would be here. Notice that they're all equally spaced. They're all different by an angle of 120 degrees. So kind of a neat thing. There's some more patterns that I could show you, but we really need to practice this formula one last time. So are we okay with this one? I promised I would go back, share with you that formula again. This is a good one. I would be ready for something like this. Again, I try and make these work out a little bit on the nicer side, but we do have one that's challenging coming up in the form of example J. That would be doing the same thing except in radians. So it's just because I chose to work this in degrees. If you have to do radians, then this would be it. In fact, I'll give you a choice. On this next one, do you want me to work in radians or degrees? Radians? Okay, fair enough. So we're going to use this formula then. This time we want to find the complex fifth roots of -10i. So let's move on to do that one. Complex fifth roots of -10i. Well, let's first of all write this in polar form, and to do that it might help us to realize that that's really equal to 0 minus 10i. That's just a different way to write it. If I were to graph this, where would it be? What, where's it going to be? Yeah, it's going to be on the y-axis. It sounded like Sean. Thank you. All right. So that's going to be down here. I need to know two things. I need to know the radius, which is this, and I need to know the angle, which is this. Both of these are things that should not require any calculation. And let's put theta in degrees, or excuse me, not in degrees, but in radians. Start by telling me what r equals. How far from the pole is it down to this point? That would be our theta, thank you, 3 pi over 2. But how about r? What's r? Almost. R is just going to be the distance, not negative or positive. It's just going to be 10. So I can write this as 10 times cosine of 3 pi over 2 plus I times the sine of 3 pi over 2, like that. And what the problem is asking us for is find the fifth roots of 10 cosine of 3 pi over 2 plus I times the sine of 3 pi over 2. this is your n. Last one, n was 4. Here, n equals 5. What's this telling me? That's my r. R is 10. And that is my theta, which is 3 pi over 2. So those are the things that I need to plug into my formula. So let me go back to that formula here. Yeah, right here. Let's make that a little bit bigger. There we go. So it's going to be the 5th root of 10 times cosine of theta, which is 3 pi over 2, plus 2 pi k divided by n. So, wow, a lot going on here, but it's this formula that we're going to fill in. Let's do it. So I'm going to start by writing it as z sub k is going to be the 5th root of r, which is 10, times a cosine of theta, which is 3 pi over 2, plus 2k pi divided by n, but n in this case is 5. So that's the hard part right there, is getting all these things in. You've got your 5th root of r, you've got theta and n. This is just kind of a repeat. It's just I times the sine of all of this. So 3 pi over 2 plus 2k pi over 5, like that. Now you might want to clean this up before we start working on this. It's up to you. Trying to think of a convenient way to clean this up. This is also going to be for k equals 0, 1, up to what? What's k going to go up to? Almost. It's going to go up to n minus 1, so 5 minus 1 is going to be up to 4. All right. This is kind of ugly in here, especially with the 3 pi over 2. What you can do, let's see, I'm just going to do this off to the side. 3 pi over 2 plus 2k pi over 5. I'm going to do this. I'm going to multiply the numerator and denominator by 2. So 2 over 2. When I do that, am I changing the value of this? No, because I'm multiplying essentially by 1. But if instead of canceling the 2 and the 2 here, if I distribute the 2 in the denominator, I get a 10. And in the numerator, I get 3 pi plus 4k pi. And that might be a little bit easier to work with. So let me clean up my formula here. Z sub k equals 5th root of 10 cosine of 3 pi plus 4k pi over 10 plus I times the sine of 3 pi plus 4k pi over 10. Whew, a lot of work to get there. I'll pause here for a second. If there's something that you're a little unsure about, maybe I went over too quickly or forgot to go over, let me know. No, doesn't. So, all right, so let's try and find z sub 0. Z sub 0 is going to be the 5th root of 10 times a cosine. Now if I put in a 0 for k, I'd have that 0, I'd have just 3 pi over 10. Plus I times a sine. The angle has to be the same, so it's going to be 3 pi over 10 again. Let's keep going. Remember, we want to do this for k equals 0, 1, 2, up to 4. I don't know why I didn't just write to 3, 3, 4. So z sub 1, again, is going to be the 5th root of 10. Cosine, this time if I put a 1 there, how many pi do I have in the numerator? Yeah, 7. 7 pi over 10. And keep going. Z sub 2, 5th root of 10, cosine of, let's see, that'd be 8 plus 3 is 11, pi over 10 plus I times the sine of 11 pi over 10. And maybe you're starting to see a little bit of a pattern here. Each time I increase k by 1, what happens to the numerator? Yeah, increases by 4 pi. So increase that by 4 pi, what'll I have? Cosine of what? 15 pi plus I times the sine of 15 pi over 10. And then the last one, z sub 4 is going to be the 5th root of 10 cosine. Someone else, tell me what the last angle is going to be. Maybe a voice I haven't heard yet tonight. 19 pi over 10, thank you. And if you needed to, you can get the decimal approximations that you might want from this. So, don't worry, I promise not to give you anything higher than a 12th root. All right, I'm kidding. I do try and construct these to be a little bit more user-friendly. That one was a tough one, but you are going to see some tougher ones in your homework, so I hope this helps. If there's something about this you're not sure of, let me know. You can at this point, if you needed to write it in the form of, say, a plus bi. Now sometimes on the test I'll say pick one of them and write it as in the form of a plus bi. This is what you'd have to do. First of all, we need the 5th root of 10. So let me show you how to find the 5th root. You're going to hit the math key, then the 5th option down offers you the chance to do the 5th root of 10, and then get out from underneath the root. I'll do cosine of 19 pi divided by 10, and bam, I get 1.507. If I want to repeat that for the sine, I'll just hit second and then enter and go back just a little ways, and where the sine, where the cosine begins, just type over it with a sine. Make sure your calculator's in radian mode and you should be good to go. But that's how you would approximate it and turn it into rectangular form. You could also turn this into exponential form. Remember, exponential form would be r e to the I theta, where theta is in radians. So that'd be the 5th root of 10 e to the I times 19 pi over 10. Woohoo! Nice. Oh, you know what? Here's a quick thought. I think this might work. I don't know. Let me try something real quick here. I'm going to put my calculator in this mode right here, a plus bi. And then I'm going to try and calculate, where is it? Try and calculate the exponential form of this. So let's go back to math, option 5, 5th root of 10, and then e to the I. Now I is built into your calculator. It's right above the decimal key. So I times 19 pi divided by 10. Let's see if this gives me the complex number that I was looking for. It doesn't look quite like what we just got, does it? The first part does. Is the second part the same? Let me go back. Yeah, second part's the same. Oh, so cool. That worked. That actually worked. It gave us both parts of this. If you look back, we've got the real part here and the imaginary part here. Notice there's an I at the end of this, so that's your imaginary part. So yeah, that worked. Nice. Cool. And here's the key history and all that kind of stuff. I think the big thing that you are going to need to do if you wanted to do this is change your mode from real to A plus BI. That's going to allow complex numbers there for you. All right, pretty cool. How about a break here? Any last minute questions? All right, good luck.